So we'll do the same kind of test with 11 multiple choice and a couple of problems. The problems will be some calibration example, whether it be standard additions or external standards. And then the second problem will be similar to the first, but what will be is I will give you then the sort of results of a calibration equation and then ask you to propagate the uncertainty. I don't want to build the propagation of uncertainty on top of what you did on problem number one, because what if you totally screwed that up? Okay, so I don't want double jeopardy on there where if you can't get the first part right, they have no hope of getting the second part right. I want to see that you can do the first part, and then I'm going to kind of give you an example of something that you would have done on the first part and say, now tell me how certain you are in X. Give me your confidence intervals and so on. Okay. So those are the two parts. And that'll be worth, like I said, a substantial part of the exam. I think you started first, and then I'll get to review.
Number 15 under homework.
Yes.
I'm just trying to understand how you got your answer, and then try different ways.
Can I look at it?
Yeah. That one.
Number 15.
Yes.
Okay, so this is a dilution equation. So we have an aliquot of a certain concentration standard diluted to a larger volume. What's the RSD of the result? Okay, so let me just go ahead and write this out on the board. First of all, this is an equation that you should know from your chemistry background, and that is basically the equation for dilution. So who can tell me what for serial dilutions? What is the equation that we use for serial dilutions? M1V1 equals M2V2, and this is typically molarity, but it's anything in concentration. It could be milligrams per liter, and in this case we have something milligrams per milliliter. Okay, so our M's would be our concentrations, and then the V's would be the volumes. And so we have it says a 0.5 milliliter aliquot of 0.1. So we have 0.1 here, 0.100. And then parentheses 5 milligrams per milliliter for M1, and then we have 0.500. And then we have M2, and then our final volume, 1,000.03. milliliters. Okay, so it's diluted to a liter. So this is our problem, and what we want to know is what the standard deviation or relative standard deviation is going to be for our result. So let's go ahead and do this calculation. It's not asking for what the result is, but let's just go ahead and do it just to make sure that we know. Now, M2 is equal to that divided by 1,000. So and I'm showing the uncertainties in parentheses. It makes it a little confusing because it looks like it's multiplication, but I just wanted to show you where the uncertainties are. You can kind of see that this is 5 parts in 1,000, so that's pretty small. This is 3 parts in 10,000, because this is 3 in that decimal place. And then this is 4 in that decimal place, so this is 4 parts in 500. And so this is going to be the one that limits our uncertainty. So let's see if we can figure this out. So this is going to be so 0.05. And so the question is then, what's our uncertainty? So we need to propagate the uncertainty. Now this is what type of problem? Obviously it's multiplication and division. So what's our uncertainty equation for that? So for multiplication and division, the uncertainty in terms of our relative standard deviation of our result is the sum of all the squares of the individual uncertainties. Okay. So we take the relative standard deviation of this piece and square it, the RSD of this piece and square it, the RSD of that piece and square it. And then we add all three of those together, and then we take the square root and we get the RSD for our result. Scoot this over. Okay. And so I write it out. And so this is point. I'm going to do this first one here. 0.0005. Over 0.100 plus. Yeah, you can see that. Can you see way over there on the right? Okay, is that helping? Okay, so does everybody see where these fractions came from? I think, is this the thing that was difficult? Yeah. So this, if you're looking in the problem, you have all of these numbers given with uncertainties in parentheses. And the uncertainty for this 5 right here is that place value right next to it. And so that's 0.0005. 0.0005. That's the uncertainty for the concentration in milligrams per milliliter of the initial aliquot over 0.1. Okay. And so that is the RSD. That's the relative standard deviation for the concentration, M1. This is the RSD for the first aliquot, the volume, V1. This is the uncertainty for the dilution volume, the 1 liter. Okay. Now I can look at this. In fact, I could probably look at the original problem and say that this is going to be the largest uncertainty. And so my result is probably going to be just that number, this 4 over 500. So just let's take a guess. Someone calculate 4 over 500. So my estimate is what? 0.008. And there's one on here that's 0.009. Okay? So that's a pretty good guess. Okay? Let's go ahead and calculate this and see what it turns out to be. Okay. So if someone would take 5 divided by 1,000, so that would be 0.005 squared. And then 4 divided by 100. No, 4 divided by 500. So 4/5 is 0.8. So 0.08. Is it 0.08? Zero. So what's it, 4 over 500? 0.008? Yeah, that's what we just calculated. Yeah, thanks. And then 0.3 divided by 0.0003 squared.
does come up to 0.009.
Mm-hmm. Yeah, because think about this. We've got 0.008. That's the largest of these three. We square them. When you square the tiny numbers, they get even tinier. And so this one gets tiny less. You add all those tiny little numbers to this number, and it doesn't change it very much. And then you take the square root, you're back to where your estimate was. Yes?
So in the practice exam, this is in the multiple choice section, but this would be one of those problems you have to get instead, or would it be in a multiple choice?
This would be just like this in a multiple choice.
Okay.
Yeah. Notice how doing it this way, it takes quite a while. Okay? There's a lot of numbers here. But looking at the problem, you see this is going to be a really low uncertainty. This is going to be a very low uncertainty. This is your biggest uncertainty. And so if you're estimating your uncertainty, you can look at the largest one. Remember, we're just talking about where the uncertainty is. The largest uncertainty is going to be the one that really hurts you. You don't care about this one, right? It's 3. When I say 3 and 10,000, right, I'm just moving the decimal place to get rid of it and just saying, okay, it's 3 divided by that huge number, 10,000. That's so small. That's not really adding anything to your uncertainty. Now, this is the relative standard deviation. That's a fraction. That's a unitless fraction. What is our uncertainty in concentration, though? So this is equal to, I'll say, S M2 over M2. Right? That's our uncertainty in M2 over M2. So what is SM2? Well, that's equal to, we calculated M2 right here. Is that correct? I didn't really get that. So that's equal to SM2 over 0.00005. So I'm going to take this number times that number to get this. So if you have the relative standard deviation, you need to be able to get to the uncertainty. And so this going from RSD to S or RSD to M, these are just fractions. It's just a single fraction. You should be able to do that. So SM2. Can someone multiply this by that for me?
40. There's 6 zeros. Yeah.
Okay.
And then 4.
5 or 4?
4, 5. Yeah,
4. Okay. And then this is milligrams per milliliter. So if we're going to write that out, this has got 4 zeros and a 5, and this has got 6 zeros and a 4. So we could write this M2 is equal to 0.000500, and then put the 4 in parentheses there. Does everybody see how that works in our reporting? Right, so here this 5 goes right here. Do I have? Yeah.
Yeah.
Actually, it should be one more 0, shouldn't it? Yeah. So.
No, there's a 0 in front
That's it. One more 0 here.
Yes.
5, 0, 0,
Yeah.
and a 4 in parentheses. So that'd be one way to report our data. Okay. We could write it in scientific notation, and we could say 5.00. Let's do that. So 5.00 times 10 to the minus 1, 2, 3, 4, 5. And then we could say plus or minus. I'm going to put the 4 next to here. So 4 times 10 to the minus 5. So that would be maybe a nicer way to write it, and it's in scientific notation. But looking at that problem, the fastest way to do it would be to look at all 3 of those uncertainties and take 5 divided by 1,000, 4 divided by 500, 3 divided by 10,000 and see which one's the largest. That was the largest, so that's going to be the estimate of the relative standard deviation of the result. And you 0.09, move on, 0.009. You say, well, I got 0.008 by estimating with just one number. There's a chance that these others are going to add a little bit to it, so it makes sense that it would be a little higher as 0.009. You see how this, that would be even a better skill, I think, for you to be able to estimate these things. It'd be nice to be able to calculate them all the way out, but even better, you can do the calculation. Can you estimate? That's great if you can estimate. Yes, now.
Question number 8.
Okay.
So,
do you mind if I keep this?
Oh,
Okay.
So for significant figures, the rule of thumb for the subtraction is that you keep the lowest number of decimals. So then
Yes.
the correct answer would be 2.2 times 10 to the negative 2, and that's not an answer listed. The test bank answer says that it is 2.20.
Why do you say it should be 2.2? Because the decimal place in the 2 times 10 to the minus 6?
Yeah.
But the thing is, they're at different powers of 10.
Mm-hmm.
So you get them in the same power of 10, and then whatever the smallest, I would say the largest place value is limiting. So let's do that. So I'm going to take these two numbers. They're written in scientific notation. So I have 2.2 times 10 to the minus 2, and I'm subtracting 2.0 times 10 to the minus 6. And of course I can't do that because of these powers of 10. So I'm going to get them in the you really just need them in the same power of 10, but that can be confusing. And if you just try to move the decimal place, the chances of you screwing it up are enormous. Okay? So let's just get rid of the scientific notation altogether. So this is 2.2 times 10 to the minus 2, so that means we're going to move that decimal place to the left, so 0.022. Does everybody agree with that? I've moved it to the left 2 places. Okay, and the next one is 2.0. Oh, I should put this up here, 2.20. Okay, so I have out to that 2.20. I got to keep that 0 because it's significant. And then I'm going to subtract. And now I'm moving at 6 decimal places. So I have 5 zeros. 1, 2, 3, 4, 5. Yeah, 5 zeros and a 2. 0. And so when I look at this is the limiting place value. And so then I drop that line down there. Now, if I were to do the subtraction, we can go ahead and do it. We can start borrowing and so on. So I'm going to draw this line, but then I'm going to put some zeros here. And so that's going to be 8, that's going to be 9, that's going to be 9, it's going to be 1, 2, 0. Okay, but then that dashed line tells me where to round. And so I round back up 0.0220, and so that's going to be my result. If I subtract this tiny number from that, and I'm already uncertain at this digit, then I don't know that I've subtracted anything. And so the key is to get them in the same power of 10. We could have converted the 10 to the minus 6 to 10 to the minus 2, and so our decimal place would be here. We would have gotten the same result. And so it's a good question, though, because what we're doing is we're trying to subtract such a tiny number that we don't even miss it. And so it's as if we haven't just subtracted anything. Yes?
Question 13.
Oh, yeah, I heard some people asking about this one online, so I'm glad you brought it up.
Yeah.
Yes. In weighing, and this also applies to titrations, a single mass measurement or a single volume measurement, like in a titration, you can't actually make a single measurement. You're always doing differences. And so when weighing something out, even though you've hit tare and it goes to 0, it actually fluctuates, right? And so there's uncertainty related to 0 and there's uncertainty related to the mass number. And whenever you're weighing something, you're subtracting 0. But there's uncertainty in 0 and there's uncertainty in the mass number. So we have addition and subtraction. So you might say we have m minus m tare to give our net result equals m net. And so whenever we're measuring out using a balance or scale, we're actually taking a difference. And so in those cases, then the uncertainty net squared is equal to the sum of all the uncertainties squared. So this is for addition and subtraction. We use this error propagation formula. Now, knowing that those sort of the page that has all the uncertainty formulas, this looks a lot more complicated, but it's equivalent to this. It's just summing all of the pieces that you're subtracting and adding together, and their uncertainty. You just square those uncertainties, add them together, and that's the result uncertainty squared. Now, you could take the square root of both sides, and that's where that square root comes from. So let's go ahead and do that. And it was 0.5. Where is that? 0.5. So 0.5 squared plus 0.5 squared. So that's where it comes up to 0.7. Because there's two 0.5s. And these were grams.
Yeah.
But it's just also, I put that in there not just to show you how to do the addition and subtraction, but also to drive home the point that every kind of mass measurement is really a difference. And so that you have two mass measurements, even though you think you're just making one. Same with titrations. Whenever you're calculating the volume delivered, then you have the top number subtracted from the bottom number. And so you've delivered two volumes. Your uncertainty and your titration will be two of those uncertainty values. Squared, added together, and take the square root. So that would be the final uncertainty in your volume difference measurement. Next. Here, Melissa. Thank you. Sure. Okay, so this is asking about the Z transform on the data set. So in order to do that, we'll have to find the mean and standard deviation of that data set. Okay, so we have xi, that's 10, 0, 0, 10, 0.35, and 20. So add all those up, we have 35 here and 30. Divide by 3. 40. Thank you. What's our mean?
13.45.
Okay, so 13.45. So now xi minus x bar. So that 3.45 3.1. We're going to square these, so it doesn't matter what the sign is. And it'll be 6.55. Can you check my math on that? I'm taking the differences. These are deviations from the mean. And now I'm going to square all of those. I need your help on that one.
Second one is 9.61.
9.61.
Um, 11.9 for the first one.
11.9.
9.
Okay, and then the last one?
42.9.
Okay. So those are my deviations. I'm going to add all those together. So we're going to sum the deviations. Point 41. Then I'm going to divide that by 3. No, minus 1. 3 minus 1. So this is not a population. This is a sample. So I'm going to divide that by 2. So that's 32.205. So this is my standard deviation. Oh, I'm going to take the square root of that. So someone put that in, get the square root.
5.67.
Louder, please.
5.67.
Okay, so that's S. So that's how you calculate the standard deviation. I do it in table format because I think it's the most organized way to see it. So we have the mean. So this is the mean, X bar. This is the standard deviation. And what we want to know is the Grubbs transformation or the Z transformation. So what that means is that we have the difference in the projected outlier from the mean. And then we scale that or divide by the standard deviation. So Z is equal to 13.45 minus 20, or vice versa. Just to feel it. Take the square, the absolute value if you want. 5.67. So 6.55 over 5.67. 1.2? Okay. And so that's the answer here on number 18. Now, I'm going to ask you one more question. Is it the next question? No, I didn't. I missed an opportunity. Okay. So there's your Z value. Okay. And my question is this an outlier at 95% confidence?
I think that question says something else.
Is it?
Yeah. Well, there's Dixon's Q test.
Yeah.
Yeah, okay. So it's a different way of calculating it, but yeah. But let's go ahead and take this. We've got a Z value of 1.2, and we want to know if this is an outlier at 95% confidence. What would be the Z critical value? So we're asking, is 1.2 greater than Z critical at 95%? Now, where do I get that table? This is actually that value. This is actually one of the ones that you probably have memorized by now because we've talked about it so many times. When I'm calculating the 95% confidence limits, what do I multiply my standard deviation by?
1.96.
1.96. That's what that is. 1.96 is my test value for 95% confidence. And so if this 20 were farther away from the mean when scaled by the standard deviation, farther away than 1.96, there'd be less than a 2.5% chance that random noise would give me that number. See what we're testing? We're saying our limits, our confidence limits, if we wanted a 95% confidence limit around 13.45, would be 1.96 times our standard deviation. And we're just seeing if 20 is that far out. Okay. And it's not. It's 1.2 out, and 1.96 would be our cutoff. So if I wanted to plot this, our mean would be 13.45. What would be our 95% confidence limit? It would be 1.96 times this. So let's go ahead and multiply this by 1.96.
11.1.
11.1? Okay. So it would be 13.545 plus 11.1, correct? Okay. So that would be 24. So 24.55 would be the high side. Let's take 13.45 and subtract 5.6 times 1.96. So let's subtract our confidence interval. It was 11.1, so we're going to subtract that. It's going to be 12.35.
2.35.
Oh yeah, thank you. 2.35. So our standard deviation is pretty big. That's our 95% confidence range. And 20 is right here. So it's not an outlier. So this is kind of complicated, calculating your whole confidence interval and everything, when you could just calculate this z value and see if it's greater than 1.96. That would tell you if it's out here. So that's all you're doing with the z transform, is you're just saying, is it outside my 95% confidence interval? If it is, you'd say it's an outlier. Yes.
Okay, so basically you're saying you multiply the standard deviation times 1.96 and what's that?
And so this right here is giving us, if we drew a nice, beautiful bell curve around there, then the 95% confidence interval, the inside of this is 0.95. So all this area would be just what random variation we give in our data. And then out here is 2.5%, 0.025, and over here is 0.025. And all we're doing with the z transformation is seeing is there's 3 data points and one of them looks odd. Is it outside our confidence interval? And the way you do that is you calculate the mean, you calculate the standard deviation, and then you take that suspect data point, see how far it deviates from the mean, and then divide by your standard deviation. And that gives you this thing called a z-score, okay, or the z-transform value. And then you just compare that to your 1.96, which is your z value for 95% confidence. They're all interrelated. You could use this z value times your standard deviation to give you your confidence interval and see if that data point is inside or outside. It's the same calculation. It looks different, but it's the same calculation.
I was just trying to make the connection between the 1.96 and what you drew up there.
Yeah, and so this 1.96, I used that times the standard deviation to tell me how fat this curve was.
Okay.
Yeah. So this 5.67 is actually the distance from the inflection points. So notice how this curve is curving down, and then at some point, the inflection point, it stops and starts curving up. And your standard deviation on a normal distribution is where those inflection points are. And so if you drop those inflection points straight down, that would be plus or minus 1 standard deviation. And that would cover 0.64% of the area. But that's a 64% confidence interval. And we really don't like that. We'd like 95% confidence. So we almost double it. We multiply by 1.96, and that gets us out here to where we only have 2.5% on the high and low sides that would be excluded. So it's all based on that Gaussian distribution, and the z values are just it's just the values that give us these different areas under that curve. The one that we use so much that you should memorize it is the 1.96. That's the z-value for 95% confidence. That was great. Hit save on the video. I think if you understand this, that's huge, because then it's not just what equation do I use. You know, but you understand that this curve is given by the random variations.
So number 17 is actually an outlier. It'd be the same.
It'd be the same thing, only you've just taken the gap over the range, and so you just have a different number down here, and you take the gap. So it would be this difference, because this is 20 and that's the nearest neighbor, so that's the gap. And the range is the full range, so 20 minus 10. Yeah. In that respect, it's easier because it's real fast to just use your data and say, here's the gap, here's the range. I don't have to calculate the mean, I don't have to calculate the standard deviation. I just take the gap and divide by the range and compare it to my Q table. So the Dixon Q test in that respect is faster, but I think there's more pedigree associated with the statistics of the Z transform. So I think that sort of I've determined that people favor the Z transformation because it's based on a normal distribution. Now the Dixon Q test, the critical table is based on a normal distribution as well, but it may just be personal preference, flavor of ice cream, which one you like. Yeah. What does skewness tell you? Yeah, whether the data tails. If it's a positive skew value, it tails to higher results. If it's a negative skew value, it tails to lower results. In kurtosis, it's how peaked the data is, if it's peaked in the middle or flat topped. Yeah. What's bimodal data? Yeah, so you have two distributions being assumed to be one, and that can lead to errors. Yes?
So in reference to kurtosis, do we require that whether we want it to be more?
We want it to be kurtosis of 0, where it follows a normal distribution. So it's comparing the data to a normal distribution and saying it's either more peaked than a normal distribution or more flat than a normal distribution. So a 0 kurtosis would be a normal distribution. At least, it might still be skewed, there may be a skewness value, but at least it's not peaked relative to a normal distribution. So we would like to have a 0 kurtosis and a 0 skew. But it's, very, I guess, unlikely to get exactly 0. Especially if you're just collecting a samples data set, not a full population. So if you have 5 or 6 measurements, the chances of that being normal are pretty low, just because you've got 3 measurements that are the same and one over here and one over there. It's going to be hard to approximate a nice smooth Gaussian curve with 5 data points. Yes.
On the dendrogram,
Yes.
you emphasize major groups.
Yes.
I can ask this like for the other swans.
No, just trying to see if, the groups is kind of subjective, right? If I said how many groups are here, if I were to do that, I would pick a very clear result. But again, clear to me. Would it be clear to you? I don't know. But I could certainly ask you, from this dendrogram, which 2 points are the closest? Okay, and of these 4 choices, which of these pairs of points are farthest away? And so you would want to see like A1 and A5 are connected like the 5th level, but A1 and A10 aren't connected until way at the top. And so A1 and A10, whatever I just said, are the farthest away because they don't get pulled into a group until way late. So if you think of the dendrogram, it's like you start at the bottom and you connect the first 2 data points, and then add a 3rd, and then a 4th, and so on. And so that's early. And then the last few to be connected are late in the game. They're far away, or they would have been connected sooner. So you could compare those data points and say, okay, all of these, which pair was connected latest in this exercise, and those 2 points would be the farthest away. So I think I would rather ask you that kind of question because it's objectively right or wrong, as opposed to how many groups are here, where you say, well, I think this is a group, and maybe I don't. That should make you feel better.
Looking at some of the small ones.
Yeah, and you can Google these. I mean, look at the ones that you see. Type in dendrogram and then go to images, and you'll see a bunch. And you can kind of just get familiar with all the different ways they look. That's part of my goal, overarching goal in education, is to get you to take ownership of your education. So, yes, do the things I provided for you, the practice test and so on, and try to understand why it's right. But then also, if you need more experience on skewed data or kurtosis, start Googling, start looking at other examples. I think you probably do that, but I really want you to do more of it. Find things on YouTube. It's your education. The more you learn, the better. Okay. If you feel like you're drifting and you're saying, I don't know if this is applicable, you can always ask me. Say, look, I saw this video. Is this getting too far away from the main points that you're interested in? And I'll tell you yes or no.
Will you be asking this about type 1, type 2 errors?
No. It depends on the null hypothesis and so on. So, I mean, it's in the notes if you need it. So whenever you come across that in the future, you'll know where to go. You can come back to the notes and you can look that up. Like lecture 1, way back at the beginning, we talked about 3 court cases that sort of put the overarching restrictions on what we can do in the crime lab. What were those 3 court cases? Fry, Daubert, Kumo, Tire, yeah. Which areas, what were some key words associated with each one of those? So with Daubert, what was its main point? They all kind of have something to do with admissibility, but it was admissibility for what kind of information? Scientific methods used to analyze the data. So it would be focused on scientific methods, that they were relevant and had a good pedigree that be used in court. Then what was the next one? Yeah, Fry was on expert testimony. And then, pardon?
Yeah.
Cuba was expert testimony, and then, and what did it set up? What were some of the restrictions on that? Who decides? One more time.
Each discipline within itself.
Yeah, each discipline. So you would look to see if it was published, say, in the peer-reviewed literature, and so on, or if the discipline, say, it was arson investigators, where it maybe not be something that's, amenable to peer-reviewed literature, like, say, a analytical technique, but still the discipline would be a certification for arson investigators, so that discipline would have certain criteria for training, so you would want to make sure that that person was certified by that discipline. And then what did the last court case talk about? Yes, and also it was, who was the gatekeeper in the case? The judge. Which court case really set the judge as the gatekeeper role? Pardon? Daubert. And so that's a lot of power for the judge. A lot of times they will pull the counsels and everything aside to do a Daubert hearing outside of hearing of the jury so that they can decide what gets shown to the jury. They don't want to poison the panel with something that's going to be stricken because it's very difficult to unhear something. So that would be a Daubert hearing. They would have a separate Daubert hearing on whether this is going to be admissible or not. Excellent. Just because I want to hear it, what are the three questions an analytical chemist asks? Answers. Yes. What is it? How much? And how certain? How is a forensic chemist different than an analytical chemist? They are analytical chemists, but they do things a little bit differently. So which of those three questions? They certainly say how much and how certain. But what's different about the what is it question for a forensic chemist?
We're already comparing to something.
You use the right word. Comparison. Yeah. Does this compare to a controlled substance? Yes or no? And if it is, then you would say it is a controlled substance. If it's not, you do not continue to pull the thread to find out what it is. So white powder is or isn't a controlled substance. If it's not, we're done. Whereas an analytical chemist may want to go all the way to qualitative analysis to identify what it is. So the art of comparison is really that part of the qualitative analysis that a forensic chemist focuses on. A little different than just straight qualitative analysis performed in an analytical lab. Now you may, as a forensic chemist, go all the way to finding out what it is if you're curious about that case. But a lot of times you're just saying, is there isn't a controlled substance? Is it or isn't, blood? So it's a red smudge on the floor and you find out it's not blood. I mean, you may not be interested in it if it really has no bearing on the case. So there may be some intellectual curiosities that you don't get to chase down, but that's fine. You got probably a pretty big caseload, and so you got to move on to the next thing. All right. Will y'all complain if we leave? All right, cool. Enjoy.